Welcome to physics class. Today we'll discuss more problem on classical mechanics using solution of on more problem using the Lagrangian formulation. So last class we discussed about simple pendulum and various combination, various state of simple pendulum in different state. What will be the frequency of oscillation or time period associated with the pendulum? We discussed all those things. We'll take more problem here. Another problem here. Here first problem I am going to take spring mass system. Spring mass system. So in case of spring mass system, it is written that spring and mass combination, a system combination of spring and mass. Suppose let us take a spring like this, and a mass is m connected with the spring, and constant spring constant is suppose k, clear, and spring constant is k. So if I applied an external force on this mass, suppose F force I am applying, and for the application of that force the displacement of this spring is suppose x, displacement is x. Then in this system what will be the again, if I remove this force, if I remove the external force, then it will be something oscillation will be there. And what will be the frequency of oscillation, and what will be the your equation of equation for this system. So you see, we have shown that displacement of the spring or elongation of the spring is x. So mass of the bob or that is m, and spring constant is k. So what will be the first we have to find out the degree of freedom of this system. How many degree of freedoms will be there? Only 1 degree of freedom for this bob, only 1 degree of freedom. And what will be the generalized coordinate? What is changing the displacement of the position, displacement position of the bob is changing. So degree of freedom here DOF equal to 1, and your generalized coordinate is x. Only one generalized coordinates will be there. Generalized coordinates. Now we have to find out, to construct the Lagrangian, we have to find out the kinetic energy as well as potential energy. And kinetic energy T equal to half of mv square. But here we will write in terms of position, displacement. Since x is the displacement, so the velocity will be x dot square, and your potential energy will be, what will be the potential energy associated with that spring, that all of you know, half of k, and what will be the displacement, kx square. So then Lagrangian instantly I can write T minus v equal to half of m x dot square minus half of k x square. So what will be the Lagrangian equation of motion? D upon dt del L upon del x dot minus del L upon del x is equal to 0. So your d upon dt del upon del x dot, so if I differentiate it with respect to x dot, only x dot is here, so it will be 2 into m x dot. Okay, 2 m x dot, and 2 to cancel, it will be m x dot minus what will be the differentiation of this equation with respect to x? It will be, here no x term is present, here only x term present, again 2kx. So 2 will get cancelled, and another minus sign, this minus and this minus sign will be plus sign, so it will be kx is equal to 0. So again I have to differentiate it because x dot is variable, so with respect to time it will be mx double dot plus kx is equal to 0, or your mx double dot plus k upon mx is equal to 0. So this equation is nothing but an equation of a simple harmonic motion. Since x double dot, so if I equate it, So x double dot is equal to minus k upon mx, where x is the displacement. This k and m is a constant, so acceleration is proportional to the negative displacement. So the motion associated with the spring mass system, that is simple harmonic motion, and what will be the angular frequency. So if I equate it with an equation, so x double dot is equal to, suppose, omega square x, then omega square equal to under root of k upon m, and your omega equal to omega square equal to k upon m, omega equal to under root of k upon m. So this is the angular frequency. What will be the linear frequency? T equal to twice pi by omega, so twice pi under root of m upon k. Clear? So this is the frequency associated with the spring, and angular frequency and linear frequency. This is unit hertz, here unit radian per second. In when you consider angular frequency, always the unit will be radian per second. When it is consider linear frequency, then it will be like a hertz unit. So this is simple problem. So in CSIR examination you will not get this type of problem, because this is very simple. But based on this example, we will solve some complicated example. Like now, if I say that combination of springs, it means, see, if I say combination of springs, suppose or like this, one spring is here and a mass is connected m, the spring constant, this is the point of suspension, this spring constant is, suppose, k1, and here another spring is connected here, and this is the end point. The spring constant of this spring is, suppose, k. So two springs are there connecting with a mass m. Clear? Now this is a combination, combination of two springs. So you see, here we will discuss first, we'll shift this mass slightly through a distance x, displacement x. Clear? Then if we apply an external force on the mass, and if I displace the mass and if I remove the external force, then it will be oscillation. Clear? Now here, see, I am shifting, I am applying the force on the spring along the direction of what? Along the direction of the spring, springs are like this. Or I can see I can apply an external force like this way, and I remove an external force and it will be oscillate like this. So one condition is I can apply the external force like this, and I can apply along the direction of the spring, or I can apply in the perpendicular direction of the spring. So let us first take along the direction, motion along the direction of spring. Clear? Now again, what will be the degree of freedom in this case? Only one degree of freedom. So your generalized, your DOF is equal to 1, and your generalized coordinate will be x. So what will be the kinetic energy for the mass m? Your T will be half of m, change कितना हो रहा है? Displacement x, so x dot square. And what will be the potential energy? Now this time the potential energy, the contribution of potential energy because of two springs, not for only for one springs. And for two springs, for this spring, the potential energy half of k1. What is the displacement? X square plus half of another, for this spring, half of k2 x square. Clear? So what will be the Lagrangian? Or I can simplify it, half of x square K1 plus K2. So your Lagrangian will be L equal to T minus V, half of m x dot square plus half of k, half of x square K1 plus K2. So your Lagrangian equation of motion, in Lagrangian equation of motion, d upon dt del L upon del x dot minus del L upon del x is equal to 0. So here I have to differentiate this Lagrangian with respect to x dot. So I will get 2 gets cancelled, it will be m x, and again one time with differentiation with respect to time, so x double dot, clear, and this minus sign, minus, plus a minus, and here I have to differentiate it with respect to x. So with respect to x, it will be 2 gets cancelled, K1 plus K2 x is equal to 0. Sorry, here will be a minus sign. So this minus sign and minus sign will be plus sign. So K1 plus K2 x equal to, so your x double dot plus K1 plus K2 divided by m x is equal to 0. See, again this is a simple harmonic motion. What will be the frequency of oscillation? It will be here equating with that equation, omega square equal to K1 plus K2 divided by m. So your omega equal to under root of K1 plus K2 divided by m. Clear? So this is a combination. So when the spring is elongated, when the mass is shifted along the direction of the spring, and then again it will be a simple harmonic motion. So we are getting. Now we will shift this mass along a perpendicular direction. So I will say that motion, you can pause it and you can write motion along the perpendicular direction. Clear? Now see what will happen this time. Let us take the spring constant, both the spring constant for easy for our convenience. So you can will take the spring constants are same. You can write the spring constants are different also. Then calculation will be complicated, since we have to know the concept how to solve it is. So suppose the spring is this bob is shifted within a displacement x. Then what will be the picture? When the bob is here, then this spring will be like this, and this spring also will be like this. Clear? Okay? This spring will be like this. Initially, suppose let us take the length of this spring from here to here. The length of this spring is suppose L0. Clear? So both the spring, length of the spring is suppose same, L0. Clear? See, so when the bob is displaced to this position, then the spring will be elongated. So how much it will be elongated? Initially, before displacing, the length of the spring is L, and after displacing, what will be the length of the spring? Kitna hoga? That we have to find out. So from here to here the distance is x, and from here to here the distance is L. So what will be the this length? It will be under root of L0 square plus x square from Pythagoras theorem. Similarly, from here to here, what will be the distance? Under root of L0 square plus x square. Clear? Now what will be the elongation of the spring? What will be the displacement of the spring? Kitna hoga? Initially it was L0, and finally we are getting the length of the spring is this. So final minus initial will be the elongation of the spring. So your elongation will be x L0 plus x square minus L0. So this will be the displacement of the spring, okay. So here you see again the how many degree of freedoms will be there? Only 1 degree of freedom. So DOF equal to 1 and your generalized coordinate equal to DOF 1, generalized coordinate I will say it is x. So your kinetic energy, what will be the kinetic energy? T equal to half of m because of this mass mx dot square. What will be the potential energy? Potential energy because of this spring is equal to half of k, and what will be the displacement? This. So under root of L0 plus x square minus L0 whole square. K x square na, here displacement is this, so iska whole square. Got my point? So and again since identical spring from these two are identical spring plus another term bhi hoga, so the same expression. So just I will write here 2 multiplied by half of this. So your 2 gets cancelled. Now this is the kinetic energy and potential energy. Your Lagrangian will be T minus V equal to half of mh dot square plus minus k under root of L0 square plus x square minus L0 whole square. So this is our Lagrangian for this system. Now what will be the Lagrangian equation of motion? For that we have to find out first del L upon del x dot is equal to del L upon del x dot. Here no x dot is here, so it will be 2 gets cancelled. It will be mx dot. So what will be the del L upon del x? Del L upon del x. Here no x here, only x here. So it will be your minus 1, 2, then k. 2k. This will be under root of L0 square plus x square minus L0. This term will be same. Then inner we have to differentiate. So it will be 1 upon 2 under root of L0 square plus x square. Again twice x ka differentiation, it will be 2x. So 2 gets cancelled. So it will be minus 2k and 2kx, and since it is denominator, this if I divide this, it will be 1 minus L0 divided by under root of L0 square plus x square. Got my point? So you can pause it and we can write it. Clear? So what will happen next? See, so therefore I can write down the equation of motion. So in the Lagrangian equation of motion, d upon dt del L upon del x dot minus del L upon del x is equal to 0. Del L upon del x dot, so I have to differentiate with respect to time, so we will get mx double dot, and minus and this minus sign, it will get plus sign. Clear? So we will get minus and minus plus sign. So 2kx 1 minus L0 divided by under root of L0 square plus x square, that is equal to 0. So this is the equation of motion for this system. Clear? Now you see, so if I take, so we cannot so if I take this small oscillation, this oscillation is very, very small. When this oscillation, so we have to compare with something. So if I say for a small oscillation, what will be the expression, whether it will be a simple harmonic motion or anharmonic motion, then we have that we are going to find out. So suppose for a small oscillation, इसका मतलब क्या है? Small oscillation means this displacement is very, very less as compared to the length of the spring. So it means x is very less than L0. Then what will happen? So I can rewrite this expression m. It will be x double dot plus 2k by m x, okay, 1 minus, you see, can I write like this? So 1 divided by, so if I take this L0 in the denominator of this expression, it will be under root of L0 square. So and this will be 1 plus x by L0, x square by L0 square, and half is equal to 0. So x double dot plus 2kx upon m 1 minus, so it will be, say I can write it 1 plus x square L0 square to the power minus half, that is equal to 0. Clear? So if I expand it binomially, because if I expand it binomially, x square divided by L0 square, since x square is very less than x is very less than L0 square, so x square term less than one quantity, if I square it, it will be more less. So other component, the higher component will be very less, so we can omit those components. So x double dot plus 2kx upon m, 1 and 1, so you see 1 minus 1, it will be minus 1 minus 1, it will be, yes, minus half x square L0 square, that is equal to 0. X double dot 1 gets cancelled, x double dot minus 2kx upon m, x is again 2 gets cancelled, x and x cube, m L0 square, this is equal to 0. Let me see, we have show whether this sign is plus sign or minus sign. So let me see. Okay, see here this sign will be plus sign. Why? Because once I expand it, 1 minus will be here, so this like this, and neglecting the higher term, so minus 1 and this minus a, it will be plus sign. Then you see, this is our final equation. See here, acceleration is not proportional to the negative displacement, is proportional to what? Cube of displacement. So this is not a simple harmonic motion. So what we will say, this is not S is M. That means n harmonic motion it is, or n harmonic oscillation. So this, many times this example was asked in CSIR NET or JEST or TFR examination. That is why I have taken this example. So this type of example can be asked in your CSIR examination. Okay, so we'll see more problem on Lagrangian formulation, then we will go to our next part. So you can pause it and you can write it. Okay, so another your problem, that is Atowar machine with light pulley. Okay, first we will discuss Atowar machine with light pulley, then we will move to Atowar machine with heavy pulley. So Atowar machine, this problem is suppose one point of suspension, and here a pulley will be there like this, a bob, another a string, another bob. So this is the pulley. Okay, the mass, I can choose mass. This mass is m1, and this mass is suppose m2, and the total length of this string, length of the pulley, length of this machine, or length of the string is suppose L. Length of the string is suppose L. Clear? Okay. So I can write this m2 is greater than m1. So when m2 is greater than m1, so it will come down and it will go up. So after some time, after displacing these masses, so let us consider from here to here, this distance is y. Clear? Then what will be this distance? कितना होगा? Again this pulley is light pulley. इसका मतलब ये है, when the pulley is light means massless pulley. So if it is a massless pulley, then the moment of inertia associated with this pulley I can write 0. Clear? So massless pulley. So when it is massless pulley, but pulley having radius r, what will be the radius of this pulley? It is having radius r. So what will be this distance? So total distance from this to this is L. From here to here it will be y. So again I have to find out this to this distance. But total distance, what I can write, this L is equal to from here to here y, again this distance, again this path. So when the radius is r, this path is y plus pi r, and from here to here, clear? So L plus pi r and this distance. So we have to find out this distance. Let us take it is x. Clear? So this distance will be your x, will be your L minus pi r minus y from here. So it will be your L minus pi r minus y. Clear? Because we have to find out the individual potential also. From this height we have to know. Achha. What will be the degree of freedom? Only one degree of freedom. And what will be how many generalized coordinate? Only one generalized coordinate, that is equal to y. Clear? What will be the kinetic energy? T equal to half of m1. Displacement is y, it will be y dot square. For this, the kinetic energy half of m2. See, this L is fixed, constant, pi r constant, only variable is y. So if I take dot of this final of the whole quantity, the dot of this 2 will be 0 contribution, only minus y. इसका जब dot लेंगे हम, it will be again y dot square. Clear? Now the potential energy, or I can write T half of m1 plus m2 y dot square. So potential energy V equal to C. So if I set the reference of reference level potential energy 0 here, this is the reference level. From here to here, again the below the reference level it will be minus m1 z and y. Clear? Again from here to here plus, but here since negative in negative coordinates, so it will be minus m2 z L minus pi r minus y. So these are the potential energies. Now what will be the Lagrangian L equal to T minus V is equal to half of m1 plus m2 y dot square. This minus sign and this minus sign all will be plus sign, plus m1 z y plus m2 z multiplied by L minus pi r minus y. Clear? Now we have to find out Lagrangian equation of motion for that del L by del x dot. Okay? Or directly I can write d upon dt del L by del x dot minus del L by del x is equal to 0. So del L by del here, sorry, it will be y dot and del L by del y. So here y dot with respect to y dot, it will be 2 gets cancelled, it will be m1 plus m2, and again I have to differentiate with respect to time, it will be y double dot, and minus this, clear, minus this with respect to y we have to find out, so minus m1g, again with respect to y we have to find out, we have to differentiate it, all the contribution because of L and pi r, these are constant, it will be 0 and it will be minus a, so let us write here a minus sign, and this is minus m2g, okay, m2, yes, m2 clear, okay, m2z, that is equal to 0, so you can pause it and write it, y double dot is equal to here z, I can take common, m1 plus m1 minus m2 divided by m1 plus m2. So this is our expression. The acceleration. This is the acceleration, final acceleration, and this is the solution. Now you see, if I say that, so if I say this pulley is not light, this is heavy pulley, so what will happen? If it is a heavy pulley, what will be the kinetic energy here? Kinetic energy T equal to half of, we got m y dot square plus half of m1 and m2 y dot square. What will be the potential energy? Kinetic energy this, clear? But we got, when it is a heavy pulley, it is not massless. The mass is suppose m. If the mass is m, there will be the, because of heavy pulley, this pulley another energy will be associated because of this pulley, that is kinetic energy of this pulley. So kinetic energy of this pulley will be your half of I omega square, kinetic energy associated with a